Hello, welcome to another module in this massive open online course. In this module, let us start looking at binary phase shift keying. So, we want to look at this digital modulation scheme which is known as binary phase shift keying. Okay. So, what I want to start looking at is a different modulation scheme which is termed as binary phase shift keying, also termed as, also we can call this also abbreviated as rather BPSK. Okay, this is abbreviated as BPSK, and this is basically, it's a digital modulation scheme. It's one of the several schemes for digital modulation. As we already described before, similar to analog modulation in a digital communication system, we have digital modulation schemes. Okay. Now, what happens in by BPSK, the pulse shape in BPSK the pulse shape, or simply you can call this the pulse. Remember, every digital communication system employs a pulse or a pulse shaping filter. The response of the pulse is given as, well, Pt equals square root 2 over t, correct, square root 2 over t cosine 2 pi fct, such for 0 less than equal to t less than equal to t, where we know t is, this is the symbol duration, this is the symbol duration, and further, correct, we have this condition that t is an integer multiple of 1 over fc. That is t equals k over fc, where k is a integer, okay, where k is a this is an integer. That is basically, this duration t, symbol duration, contains an integer number of cycles of cosine 2 pi fct, contains an integer number of cycles of cosine 2 pi fct. Okay, so that is basically the idea, and I can represent it pictorially. It looks something like this. It's very simple. This is 0, this is t. Let's say we have something, so we have something that it looks something like this. So if I were to draw this, that will look okay. This is basically your time duration. So this is the duration, symbol duration, and this is basically your pulse, okay, and this is square root of 2 over t cosine 2 pi f c t for 0 less than or equal to t, where t is the symbol duration, and you can see this contains basically contains two cycles of the cosine waveform. Implies t equals 2 over f c. 1 over f c is the period. So, symbol duration is basically, that is, symbol duration equals 2 over f c. Okay, so, this is the symbol duration. Symbol duration equals 2 over f c. Okay. Now, further, if you look at the energy of the pulse, we can show that in this case pulse p t is normalized to unit energy. What is the meaning of that? What is the meaning of that? If we compute E p, energy of the pulse, that is minus infinity to infinity, p square t dt, that is equal to, well, 0 to capital T 2 over t cosine square 2 pi f c t dt, which is equal to 2 over t, well, integral 0 to t 1 plus cosine 4 pi f c t divided by 2 dt, which is equal to, well, 2 over t times t over 2 plus 1 over t times integral 0 to t cosine 4 pi f c t dt, and you know this quantity, or rather this integral is 0. Therefore, what is left is 2 over t times t over 2 equals 1, which is equal to your E p. So, what is shown, what we have just shown, although it is fairly obvious, is that the energy of the pulse, that is, if you look at square root of 2 over t, 2 over capital T cosine 2 pi f c t, the pulse has unit energy. So, the pulse energy has been normalized to unity. Okay. Now, A naught, we have x t equals A naught times p t. Now, earlier we have assumed that A naught belongs to minus A or plus A. Now, further, what we are going to assume is that if you are transmitting 0 or 1, for instance, let us say, let us say 1 is mapped to minus A, 0 is mapped to, so each symbol transmits, so each A naught carries 1 bit of information. Okay. Each A naught carries 1 bit of information. Okay. Now, therefore, if you want energy per bit, now a standard way to normalize the energy or compare this various schemes, various digital modulation schemes, is to basically set a constant energy per bit, okay, which we are going to denote by EB. Alright. So, this is the constant energy per bit that we are going to use throughout or across all schemes. So, we are going to denote this quantity by EB. EB equals the energy per bit, and this we are going to hold constant across the schemes. Now, therefore, if you look at this, if 0 for instance occurs with probability half, again and 1, that is information, now these are information bits. Okay. Zero occurs with probability half, 1 occurs with probability half. Now, average energy, because A naught equals, remember A naught equals plus or minus A, implies average energy equals half. Well, we are using the signal x t equals A naught times P t equals x t. So, half A square times E p, that is average energy corresponding to, this is average energy corresponding to if 0 occurs, correct. This is average energy of the signal if 0 occurs. Plus again, for 1 we are transmitting minus A times P t. So, average energy is half A square, half is the probability, remember this half is probability of probability that of the bit equals 0. So, and this half is probability of bit equals 1. When bit equals 1 with probability half multiplied by A square, which is amplitude level, times the energy of the pulse E p, which is equal to half A square E p, half A square E p, that is A square E p, and further we have set in this scheme E p equals 1. So, this is A square since E p equals 1, that is we have normalized the pulse to unit energy since E p is equal to 1. Okay. Now, if we want to set constant bit energy A square, so if you want, so this is our average energy. So, this is the average energy per bit in fact, correct. So, this what we have calculated is average energy per bit, which is A square. So, we want to set average energy per bit equal to E b, which means A square has to be equal to E b, which means A equals square root of E b. So, if A equal to square root of E b, if we set A equal to square root of E b, that is the amplitude A, remember we are using the fact that the pulse has been normalized to have unit energy. Okay. So, if we set the amplitude A equals square root of E b, correct, then the transmitted, then A equal to square root of E b, then the average energy expended per bit in this digital modulation scheme or in this binary phase shift keying scheme is going to be E b, that is the point. So, A equal to square root of E b, this ensures that average energy per bit equals E b. Okay. Therefore, the transmitted waveforms, now if you look at the transmitted waveforms, if you have 0, that is mapped to A naught equals plus A, and correspondingly we transmit x t equals A naught times P t, which is A naught equals plus A, which is square root of E b, by the way, since we are setting the energy per bit equals E b as we have just shown. So, this is square root of E b times square root of 2 t cosine 2 pi fct, of course, it goes without saying 0 less than equal to t less than equal to t, okay, which is equal to again square root of 2 EB over t cosine 2 pi fct. This is the waveform corresponding to 0. Okay. This is the waveform. Just to summarize this once again, although it should be very clear, this is the waveform corresponding to, this is the waveform corresponding to bit 0. This is the waveform corresponding to bit 0. Now, on the other hand, if you look at the bit 1, if you look at the information bit 1, then I have a naught equals minus a, which implies x t, which is basically your minus square root of E b, which implies x t equals, remember, a naught times p t minus square root E b times root 2 over t cosine 2 pi f c t, of course, again 0 less than equal to t less than equal to capital T, which is minus square root 2 E b by t cosine 2 pi f c t. This is the waveform corresponding to your bit 1. This is the waveform corresponding to bit 1, and now if you observe both the waveforms, okay, if you observe the waveforms that are employed in this scheme corresponding to bit 0, corresponding to bit 1, for instance, corresponding to bit 0, we have 2 square root E b by t cosine 2 pi f c t. Corresponding to 1, the only difference is we have exactly identical waveform, except we have a minus sign in front of it, minus 2 square root of E b over t cosine 2 pi f c t, which if you realize is nothing but square root 2 E b over t times cosine 2 pi f c t plus pi. So, if you look at the waveform for bit 1, it is exactly identical to the waveform, it is identical to the waveform, identical in the sense it is similar to the waveform of bit 0, except that it is shifted by a phase of pi. Okay. So, in this digital modulation scheme, when you look at the different information bits, the waveform of one of the bits, in fact the waveforms of each of the bits is shifted from that of the other by a phase of pi. Of course, if you take this shift by pi, right, in waveform corresponding to bit 1, add another pi to it, that is, this becomes cosine 2 pi f c t plus 2 pi, that is again cosine 2 pi f c t. So, if you shift the waveform corresponding to bit 1 by pi, you get the waveform corresponding to bit 0. If you shift the waveform corresponding to bit 0 by pi, you get the waveform corresponding to bit 1. So, the waveforms are shifted by pi, and therefore, this is a digital modulation scheme based on shifting the phases. Alright, this is a digital modulation scheme based on shifting of the phases between the waveforms corresponding to the different information bits. Further, you are transmitting two waveforms. There are two waveforms. Alright, so it's binary in nature. It's either corresponding to information bit 0 or corresponding to information bit 1. Therefore, this is binary phase shift key. Phase shifting because you are shifting the phase, binary because you are employing two waveforms. Therefore, this digital modulation scheme is known as binary phase shift key. Okay. So, you will realize that if you shift the phase of this by pi, you get this. If you shift the phase of this waveform corresponding to information bit by 1, if you shift by pi, you will get this. So, what we have, for instance, you can really see that, I mean, if you have square root of 2 EB by t cosine 2 pi f c t plus pi, if I add another pi to it, that will give you square root 2 EB by t, nothing but cosine 2 pi f c t. Okay. So, basically again we have two waveforms. Implies this modulation scheme is a binary modulation scheme plus waveforms are phase shifted with respect to each other. This implies phase shifting, or the digital modulation scheme is based on phase shifting. So, you have binary plus phase shifting, that gives rise to the name which is binary, and this is important. It is not just an arbitrary name, there is a motivation behind every nomenclature. So, the motivation behind this, calling this binary phase shift keying, is basically there are binary waveforms, two waveforms which are phase shifted with respect to each other. Therefore, this is known as binary phase shift key. Okay. And now we know what is the optimal, now we know this is what is the optimal. So, we are employing a times pt minus a times pt, we have already seen a similar scheme for instance. So, in this BPSK we are employing two waveforms, a times or a naught times, or let us put it this way, a times pt minus a times pt. The only thing is that pt equals square root of 2 over t cosine 2 pi f c t, okay, and a is square root of E b. So, we know the matched filter is given for this, the matched filter at receiver matched filter is H t equals P t minus tau, that is filter with H t, optimal processing is filter by H t followed by sample at capital T. Sample by T, and now you are wondering why we are using this P capital T minus tau. That also probably is worth clarifying, because rather than using simply P minus T, why are we shifting it by capital T? If you look at this, and this is a good plot to explain this, if you look at this waveform, this is my P of 2 cycles in 0 to t. So, if you look at P of minus t, if you simply look at P of minus t, that will simply be shifted with respect to. So, it will be from 0 to, so it will simply be from minus t to 0. Okay. So, P of minus t is from minus t to 0, and therefore, if you want to filter by this, The problem is this is a non-causal system. H of t is non-zero for t less than or equal to 0. This is a non-causal system which causes problems. This is a non-causal system. This is a non-causal system, and therefore, what we are doing is we are shifting this. What we are doing is we are shifting this by capital T to make it causal. So, shifting by capital T causal, that is an important, and if you understand the theory of linear time invariant systems, you will realize that any impulse response which is non-zero for t less than or equal to 0 is a non-causal system, all right, and one cannot implement non-causal systems, right. So, therefore, we are shifting it, advancing it by t or delaying it, that is the correct word, delaying it by t, because shift can be either left shift or right shift. We are delaying it by capital T to make it a causal system. Okay. So, let me just correct that. It is not simply shifting, it is rather delaying by t, that is important. That is, we are performing t minus t naught. So, that what happens is basically now when you delay this by t, you get this from 0 to t, this is causal. When you delay it, you get it from 0 to t, which is causal. Okay. And now, therefore, we know after matched filtering, we also know what is optimal detector. Optimal detector is, take the test static R t, which is, and compare it with the threshold R t. I am just repeating this again, once again for the sake of clarity. R t greater than 0 implies decide A naught equals A, which, or A naught equals square root of A b, which implies the bit equals 0, or if R t, let me put it this way, if R t is less than or equal to 0, this basically means decide A naught equals minus square root of A b, or bit is equal to 1. Okay. So, this is the decision rule, and we also called this as the optimal decision rule, although we did not justify its optimality. You can see by symmetry you cannot have any other decision rule which is optimal. This is the optimal decision rule purely by symmetric arguments of symmetry, and the probability of error, that is the probability 0 will be decided as 1 and 1 will be decided as 0. We have derived that, that is q of square root e square e p by n naught by 2, which is basically now you have to set in this, set A equals square root of E b and E p equals 1, and therefore, probability of error, if I denote it by P e, is equal to q square root of A square is E b over n naught by 2, which is equal to q square root of 2 E b over n naught. That is your P e, which is the probability of error of this binary phase shift keying system. Okay. And this is an important result. In fact, this is one of the most, also one of the most fundamental systems, because BPSK, as you have seen, is a simple modulation scheme, and is very efficient and very robust. So, this is the probability of error for BPSK with average energy per bit equals EB. That is the whole point, and this is a very popular and very standard result, that is the probability of error of BPSK is given as Q square root of 2 EB by NO. And remember again, just to be extremely clear, the Q function is the complementary cumulative distribution function or the tail probability of the standard Gaussian density probability density function, which is defined as integral x to infinity 1 over square root of 2 pi e power minus t square by 2 dt. This is the probability, it denotes the probability that standard Gaussian with mean equal to 0, variance equal to 1 is greater than or equal to x. That is basically what this is denoting. Okay. So, in this module we explored one of the simplest and one of the most robust, I would say popular and robust schemes for digital modulation, that is BPSK, binary phase shift keying, which uses cosine waveforms shifted by a phase of phi, two cosine waveforms, that is binary shifted from each other by a phase of phi. Therefore, it is known as binary phase shift keying. We have seen the transmitted waveform, we have seen the optimal processing at the receiver, which is match filtering, and also seen what is the resulting probability of bit error. Alright, so let us stop here. Thank you very much.